In this video, I will be discussing properties of different substances. Properties have to do with IMFs, intermolecular forces or forces between molecules. The strongest being hydrogen bond or H bond. It's between an N, an F, or an O plus a hydrogen. Then there's dipole-dipole. And that's just between polar molecules. And then London dispersion, sometimes called induced dipole. First property we're going to talk about is viscosity. Now viscosity is just pretty much how thick a liquid is. And I picture that. This liquid here be considered very viscous as it is very thick and drips kind of slowly, where this one is not. The reason why that is, think of this liquid, say, as being syrup. Now, syrup is made up of long chains of molecules. And they kind of get stuck and they roll around and they get stuck together, and it creates this rolling effect. Now, and that's what kind of makes it really thick. Now they're with long chains, or long chains experience viscosity. They have London dispersion because they are so large. Also, they can have other IMFs, and the more IMFs they have, the stronger the viscosity is going to be because the more they hold together. The next one is surface tension. The surface tension is just how well a liquid holds itself together. And a test that we commonly do for this one is the penny test. A penny. And if you pour, say, a nonpolar substance with basically no IMFs on it, the substance will just pour off the sides like this. Doesn't really hold itself together very well. But then if you pour water on the penny, it sort of makes like a bubble, drop by drop. It makes a bubble like this. Now, if we look at water up close, it has these hydrogen bonds, and they kind of hold themselves together really well, and they don't want to let go. And it all kind of pulls itself together. Where something like this with no IMFs, everything just lets go and it just kind of spills everywhere, makes a big mess. So with surface tensions, increase IMFs, increase surface tension. And that's the basics for surface tension. Then we have solubility, which is how well a solid dissolves in a liquid. You have a solubility chart for that. So this is just the basics for the solubility chart, and this is solubility in water. So these are just some examples. They're not all of them, but you've probably seen these before or have memorized them. It's the always soluble and the never soluble. So these are always form precipitates, but these never will. Now the thing for solubility, if it doesn't go with the chart, is just like dissolves like. So that means polar substances will dissolve polar molecules, nonpolar substances will dissolve nonpolar molecules. So say water, which is polar, dissolving salt, which is polar. So the water is like this, and the NaCl, Na is little because it's positive, where the Cl is large, it's negative. The positive ends of the water will be attracted to the negative Cl, where the positive Na will be attracted to the negative part of the water. And this bond right here, and these bonds right here, will be stronger than this bond right here, and will pull them apart. And that's why NaCl is soluble. Next one is miscibility. And that's how well a liquid dissolves in a liquid at all proportions. Now, this one also goes with like dissolves like. And what I mean like this, a good example is, say something non-polar plus something polar. Good common example of this is water with oil. Now the water is polar, and because it's polar, the molecules hold themselves, and they're really small. The molecules can hold themselves really close together. The oil molecules are much larger. And though they are heavier, they can't get closer together, so that denser water squeezes out the oil, and that's why it sits on the top. And that's a good example of two liquids that aren't miscible. Next one is vapor pressure. Now this is just the pressure of a gas above a liquid, and what that means is that, say you have a container and it's closed off, and you have some liquid in there, and the liquid is sort of evaporating and it's producing some gas. And the vapor pressure in there, the pressure is just how many collisions are happening. So you increase the number of collisions, you increase the pressure. Now the thing about this is the higher the IMFs, the lower the pressure. And the reason because of this is if there's high IMFs, the molecules sort of draw themselves in together into like one big clump in the middle, and there's not a lot of hitting with the outside walls of the container at all. That decreases the pressure. For an ideal vapor pressure, ideal conditions, you want to increase the temp. If you increase the temp, increase the kinetic energy, which means the molecules can move around a lot and are bumping into each other. Also means that they have enough energy to break away from the IMFs that are holding them together. Also, you want low pressure. If the pressure is very high, you force the molecules to be close to each other, and that increases the IMF attraction they have for each other. So for a gas to act most ideally, you want high temperature for high kinetic energy and low pressure. Then I have, last one is melting and boiling point, or in just general phase change. So melting is just how much heat is needed to phase change, melting and boiling. And this one's kind of basic. It's just the higher the IMF, the higher the melting point / boiling point will be. And that's just the higher the IMF, the more they hold each other together, and just more energy is needed to break them apart. Sounds kind of simple. One thing I did notice for this, that something is kind of handy to know, is that sometimes they'll put them on a chart like this. This is for a test question. And they're usually about 4 or 5. And they'll put like water in this one, and then have 100 degrees Celsius. And this is for boiling point. And then they have this substance, and this substance, and then they have like C12H26. And I'll have a boiling point, say like 112. Don't quote me on these numbers. And you'll have to explain why this one's boiling point is higher than this one's. Now, in rare cases like this with such extremely large molecule chains, that London dispersion will sometimes trump hydrogen bonding. So sometimes, in very rare cases, will trump it. Another thing that's handy to know for this one that I know I got caught up a couple times before I really understood it was the graph. These are kind of weird. Like, oh, that's way too steep. So this is solid, liquid, and gas. These are kind of interesting. Let's just use water because it's just a really basic one. So this is 0 degrees Celsius and this is 100. Okay. Now, these graphs are kind of weird. So solid ice is increasing in temperature, will increase in temperature until it reaches 0 degrees Celsius. When it reaches 0 degrees Celsius, it will remain at 0 degrees Celsius until it is all a liquid. Then what is a liquid? It will increase temperature until it's at 100 degrees Celsius. When it's at there, it will all turn to gas, and then it will start increasing temperature again. And that one's just kind of something that's really helpful to know because it's something that will probably pop up. And that is it for all the basic properties of different substances.